So welcome to section 1 of chapter 1, and we're going to look at the nature of mathematical reasoning. So it's always good to show the learning objectives as a best practice in our classroom, so I will be modeling that as I go through the lecture videos for this course. So we want to be able to identify our two types of reasoning. We want to be able to use that reasoning to make conjectures. We also want to be able to counterexample something in an effort to disprove it, so think about devil's advocate. Respond to the differences in inductive and deductive reasoning, and then use deductive reasoning to prove a conjecture. So it's really important to realize that there are two different processes related to logical thinking. There's inductive reasoning and there's deductive reasoning. When I'm talking about inductive reasoning, this is a process where we arrive at a conclusion based on an observation of a specific example. So this involves looking for patterns. So let's say you commute to work every day at 8 a.m. and it takes you half an hour. So your observation is, if I leave work at 8 a.m. because of your experience with previously, it's going to take about 30 minutes. So we're able to make educated guesses on our commute time based on our previous experience. So an example of how that works in math is, let's say we have a game show and the contestant's given a string of numbers, and you win $1,500 if you can finish the pattern. So inductive reasoning means I'm going to observe a pattern that's occurring here, and so it looks like the pattern is going to be, I'm adding 1 to 1, I'm adding 2 to 2, I add 1 to 5, I add 1 to 4, 2 to 5, so it's this alternating pattern. So because you observed a pattern, we can then say it's reasonable to say 14, 16, and 17 would be the next three numbers. So we are first person seeing a pattern here. Another example would be if I'm looking at these shapes and I'm trying to continue the pattern to the next one. In the solution to these shapes, I look at the first four figures, and the flat part goes from facing up to right, down, then left. And I've got a solid circle in those. The next sequence is going to repeat with the open circle, so by elimination or by identification of the observation, I arrive at the last level. So it's personal, first person observation. I personally observe this, therefore I think the next thing would happen. So how would I use that to make a conjecture? So previously I was giving a concrete answer. Now I want to make a conjecture. When two odd numbers are added, will the result always be an even number? So the way that I would want to use inductive reasoning here is I would want to make observations of a pattern. And then part B, I want to say how many pairs of numbers would you want to try in order to be certain that it's true. So what I like to do is I like to just start out picking a couple of them and seeing what happens. So if I add 3 and 7, I get 10, and that's even. 5 and 9, 14, that's even. And so then I kind of branch out into some larger numbers, and I'm noticing that all of them are even. Not even one of these deviates from being even. So for that reason, I feel pretty certain after 5 to 10 iterations that I'm gonna be certain enough to say that every time I add it, they're going to be even numbers. Now that number that it takes may be different for you and I. You may be less comfortable in math, and that's perfectly okay. Now let's use inductive reasoning on this example. Any 4-digit number is divisible by 11 if the difference between the sum of the first and third digits and the sum of the second and fourth is divisible by 11. Well, I've got to observe it first person, right? So I have to actually do the thing. So I've got to say, here's a 4-digit number, 1,738. So I'm going to add the first and third digit, and that's 4. I'm going to add the second and fourth digit, and that's 15. It said the difference of those two numbers has to be divisible by 11. So when I do 15 minus 4, I get 11, and it's divisible by 11. So based on that and the information I was just told, that seems like the number would be divisible. So then I go ahead and try it out, and I find out that yes, it is divisible by 11, and it's based on my personal observation. Let's try another one. So this time, let's try 9,273. So I'm going to add the first and third, add the second and fourth, then subtract those answers, and I get 11. So based on that, yeah, I think that's going to be true. And then I try it out, and yes, I'm true. So the observation is the practice problem you're doing with 9,273. That's what you're observing a pattern with. And then we've got a third example, and that also works. So after 3, I'm reasonably sure that this is going to be able to be applied across the board, especially because I kind of picked 4-digit numbers from all over the spectrum. Again, you may want to test it a few more times, but after 3, it's pretty reasonable that that pattern is going to continue. So a counterexample is like playing devil's advocate. It's one example that proves a conjecture false. So a lot of times, people need more evidence to say something is true, and you only need one example to prove something is false. So sometimes it's better to approach it from that perspective. So to find a counterexample, you got to start with something that matches the premise of your conjecture. Then you have to try and pick an instance that's going to give you a wrong answer. One counterexample proves something is false, but one example that validates the conjecture is not enough to say that it's true. So if I want to find a counterexample that proves the conjecture that a number is divisible by 3 if the last 2 digits are divisible by 3, if I want to prove that as false, I have to think of a counterexample where the last 2 digits are not divisible by 3. So the way I did this was 7 is not divisible by 3, and neither is 2. And so I had 27. It is divisible by 3 as a whole number, 27. And so I do get 509. Well, then I try again, okay? This time, I get 45. 45 is divisible by 3, and the actual whole number is divisible by 3. So at this point, I would suspect that it's true. Now, we haven't yet done anything where we see that it's false. So if we keep going, and I say, well, what if I try 36? 36 is divisible by 3, but when I actually do it, I find out that's not the case. So I find out that it's false. So the premise here would be trying to find a number that's divisible by 3, but a whole number that's not. So using 11 is a bit of a hack, because I know that 1 can't be divided by 3. If I want to make and test a conjecture, I'm going to use inductive reasoning to make a conjecture. In this example, let's say the number of sections of a circle is divided into when a given number of points on a circle are connected by chords. So if you remember, a chord is something that connects from one point to the other. So these are examples of chords. So the little segments inside the circle are chords. And I just drew a few, and I started saying, okay, if there's 1 point, I can't draw a chord. If there's 2 points, I can draw a chord. If there's, I can have 2 sections. I have section 1, section 2. If I put 3 dots, I can connect my 3 dots, and I have 4 sections. So I start to see a pattern occurring here. And so I say, let's look at the pattern. We see that a logical guess would be 32. Because it appears to be 2 raised to the power of 1 minus the number of points. So this would be something, of course, we would never ask you to draw, but it is a good counterexample because there's only 31 instead of 36. So I've proved that that's not true, because there's one thing that makes it not true. It's actually not true ever. So, all right, not true completely. So for deductive reasoning, this is the process of reasoning where we're arriving at a conclusion based on a general statement. So not an observation, based on a statement. This is based on rules, not examples, patterns, observations. It has to be using a rule. So if I want to use a rule, let's say consider this following problem. Think of any number, multiply it by 2, then add 6 and divide the result by 2. Then subtract the original number. So it's giving me a list of procedures. And it says, what's the result? I want you to do that. use inductive reasoning to make a conjecture, and then use deductive reasoning to prove your conjecture. So I'm going to do all the math. So I do all the math and my result is 3. I'm going to do all the math, get the result of 3. So I'm multiplying by 2, I'm adding by 6, I'm dividing by 2, I get 3. Same thing, pick the number 43, do all the math, get 3 again. So because I've personally observed the result is 3, I can now use inductive reasoning to say the result is always 3. But let's remember, it's a conjecture. When I use observations of patterns, those are conjectures, not hard and fast absolute truths. Now, if I want to approach this from a different perspective, and I want to attempt to use an absolute truth, then I could start to abstract this to a rule. So let's start to think of this in abstract terms. So instead of starting off with a number, I could start off with a variable that stands for a number called a. If I can show that this works for the letter a, I can show that it's true for every single number. So I'm going to say, well, instead of starting off with a number, I'm going to start off with the letter a. I'm going to multiply by 2. I'm going to add 6 to it. I'm going to divide that by 2. And then I'm going to subtract the original number, and I arrive at 3. So because I did this in an abstract way with a variable, I can now say I have proved my conjecture with deductive reasoning. So here's another example. If I want to consider the problem, I'm going to pick a number, add 50, multiply by 2, subtract the original number. I want to use inductive reasoning to make a conjecture, which means I need to try it out 2 or 3 times. And then I want to use deductive reasoning to prove my conjecture. And when I'm doing that proving of a conjecture, you definitely want to be able to do that utilizing a variable. So here's my attempt. I picked the number 12. I'm going to walk through the problem, and I get 112. Then I'm going to pick another number, 50. I'm going to walk through it and get the answer, 150. So it seems to be a reasonable conjecture that the final answer is going to be 100 more because I saw that happen twice. That doesn't prove it, but that gives me enough to say I see a pattern. So let's use that same approach we did last time. Let's use the letter A. I'm going to add 50, multiply it by 2, then I'm going to subtract the original number. And so I get A plus 100. So our conjecture was right because A is the original number, and the answer is always going to be 100 more. So if I want to compare inductive and deductive reasoning, the last 6 times we played our game, we won, so I know we're going to win. So is that observing a pattern, or is that using an algebraic rule or a rule that you always win your football games? Well, it's an observation, so it's going to be inductive reasoning. In this example, the syllabus states that any final average between 80% and 90% is going to be a B. If I get a 78% on my final, my overall average will be 80.1%, so I'll get a B. Well, the grading of a course is a rule, right? That's something you're told. It's not something you observe, so it's going to be deductive reasoning. And that is the end of section 1.